Robots in space.
Happy Pi Day, everyone. I'm Mike DiVerde, and I'm an aerospace engineer. Today, I'm wearing my Fighting Illini shirt and sipping my coffee from my Fighting Illini cup. Behind me, you see my beautiful wife and I on campus last year on our way to observe the total eclipse. Today's episode of Robots in Space, we will discuss the Illinois mission by the University of Illinois to develop techniques of fabricating and assembling composite structures in space by robots for the DARPA NOMAD program. Their experiment will fly up to the International Space Station on the Antares rocket and Cygnus robot spacecraft to demonstrate the viability of their technique. Cygnus is an expendable American robot cargo spacecraft designed for International Space Station resupply missions. It was initially developed by Orbital Sciences Corporation with financial support from NASA under the Commercial Orbital Transportation Services program. To create Cygnus, Orbital paired a pressurized cargo module, largely based on the multi-purpose logistics module, built by Thales Alenia Space and previously used by the Space Shuttle for ISS resupply. And then they combine that with a service module based on Orbital's Geostar, a satellite bus. Cygnus is typically launched using its parent company's Antares rocket from the Wallops flight facility in Virginia. However, it is able to fly on other launch vehicles. After the failure of an Antares rocket destroyed Cygnus CRS Flight 3 and damaged the Wallops facility, 2 Cygnus missions were launched with United Launch Alliance Atlas V rockets in 2015 and 2016. Additionally, 2 Cygnus missions have been launched on the SpaceX Falcon 9 rocket in 2024, with one more scheduled to launch in 2025. Now we'll watch a short video of a portion of the Cygnus robot spacecraft being handled in the factory. After that, we'll watch the launch of an Antares rocket with a Cygnus robot spacecraft headed to resupply the International Space Station.
T-minus 10, 5, 4, 3, 2, 1. We have engine start. Liftoff Antares NG-13 mission with Wallops Flight Facility. Engines at 100%. Attitude nominal. TVC's nominal. Core pressures are nominal. Engine chamber pressures are nominal. Attitude nominal. Power subsystem nominal. Altitude 10,000 feet. Attitude nominal. Core system performance nominal. Engine and TVC systems nominal. Velocity 1,100 feet per second. Attitude continues nominal. Max Q, attitude nominal. Power subsystem continues nominal. Altitude, 50K feet. Engine steady, 100%. Core, VNG3 activated. MECO slew maneuver initiated. Attitude nominal. Engines at 55% and nominal. (14,000 feet per second). Main engine cutoff.
Main engine cutoff confirmed. Standing by for stage 1 separation.
Upper ACS enabled. Stage 1 SEP.
Stage 1 separation confirmed. The next milestone is fairing separation, which will come in about 40 seconds.
Altitude, 100 kilometers. Roughly 15 seconds to stage 2 ignition.
Fairing separation confirmed.
Fairing separation.
4 minutes into flight.
Interstage separation.
Interstage separation confirmed.
Attitude nominal. Stage 2 ignition.
And stage 2 ignition is confirmed. Stage 2 is that solid rocket fuel that will burn for about 3 minutes and 43 seconds. Burnout will come about 7 minutes and 9 seconds into flight.
Stage 2 will burn for roughly 2 more minutes. Power subsystem nominal. Stage 2 attitude nominal.
Even something as common as a flame acts differently in space. We will watch 3 different videos on this. The nature of exothermic reactions and microgravity bears on the point of today's episode: fabrication and construction of infrastructure in space by robots.
Strange Flames on the International Space Station. Presented by Science at NASA. Fire, it is often said, is mankind's oldest chemistry experiment. For thousands of years, people have been mixing the oxygen-rich air of Earth with an almost endless variety of fuels to produce hot, luminous flame. There's an arc of learning about combustion that stretches from the earliest campfires of primitive humans to the most advanced automobiles racing down the superhighways of the 21st century. Engineers study burning to produce better internal combustion engines. Chemists peer into flames looking for exotic reactions. Chefs experiment with fire to cook better food. You would think there's not much more to learn. Dr. Foreman A. Williams, a professor of physics at the University of California, San Diego, would disagree. When it comes to fire, he says, we're just getting started. Flames are hard to understand because they're complicated. In an ordinary candle flame, thousands of chemical reactions take place. Hydrocarbon molecules from the wick are vaporized and cracked apart by heat. They combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually, soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy and is what makes the flame shoot up and flicker. But what happens when you light a candle, say, on the International Space Station? In microgravity, flames burn differently. They form little spheres, says Williams. Space station flame balls turn out to be wonderful mini-labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not hither and yon throughout the flame. It's a much simpler system. Recently, Williams and colleagues were doing a space station experiment called FLEX to learn how to put out fires in microgravity when they came across something odd. Small droplets of heptane were burning inside the flex combustion chamber. As planned, the flames went out. But unexpectedly, the droplets of fuel continued burning. That's right, burning without flames, says Williams. At first, we didn't believe it ourselves. In fact, Williams believes the flames are there, just too faint to see. These are cool flames, he explains. Ordinary visible fire burns at a high temperature between 2200 and 3100 degrees Fahrenheit. Heptane flame balls on the space station started out in this hot fire regime. But as the flame balls cooled and began to go out, a different kind of burning took over. Cool flames burn at the relatively low temperature of 400 to 1000 degrees Fahrenheit, says Williams. And their chemistry is completely different. Normal flames produce soot, carbon dioxide, and water. Cool flames produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth, but they flicker out almost immediately. On the space station, however, cool flames can burn for nearly a minute. There are practical implications of these results, notes Williams. For instance, they could lead to cleaner auto ignitions. One of the ideas that auto companies have worked on for years is HCCI, short for homogeneous charge compression ignition. In the automobile cylinder, instead of a spark, there would be a gentler, less polluting combustion process throughout the chamber. The chemistry of HCCI involves cool flame chemistry, says Williams. The extra control we get from steady-state burning on the space station will give us more accurate chemistry values for this type of research. Just getting started, indeed. For more information about strange flames and other mysteries in Earth orbit, stay tuned to science.nasa.gov.
Quoting from the research paper entitled Robotic Assembly of Truss Structures for Space Systems and Future Research Plans. On-orbit assembly of space structures introduce many advantages. These include inherent serviceability, inherent expandability, launch packing efficiency, ability to launch small units independently, incremental system upgrades, structural efficiency, aerial densities of 15 kilograms per meter squared for conventional hardware, essentially no increase in complexity with size, and the ability to build very large structures, for example, larger than 100 meters. The disadvantage of on-orbit assembly lies in the support system required to perform the assembly. However, the system is inherently reusable. That is, it can be applied to the construction of several components and does not increase in complexity with increasing structural size. In addition, the support system directly supports operational maintenance and repair. Once a structural concept has been defined, the actual assembly is a well-defined repetitive operation ideally suited to robotic techniques.
Think of this high-tech tinker toy as a giant recycling effort, literally. Engineers at NASA's Langley Research Center recently dug the pieces out of 6 crates that were in storage. The struts and nodes were from a research project done back in the early 90s.
You want to put it in like this?
The 315 struts and 84 nodes are part of a space structure concept for a large orbiting telescope, almost 46 feet in diameter. The idea was to design a lightweight and compactly stored configuration that astronauts could easily put together during a spacewalk.
The structure we have behind me was called the Precision Segmented Reflector. It's a 14-meter diameter. It's the primary support truss for the mirrors for the primary mirror of a telescope.
What was once a project for humans will now become an experiment for robots. Langley Human Robotics Systems researchers are working with the Goddard Space Flight Center and a university to see if machines can build the truss system.
West Virginia University and Goddard are starting to do research in robotic assembly and robotic operations in space. They have a huge facility. It's beautiful, it's new. They've got a big flat floor with a shuttle arm. They've got 3 or 4 other robots. So we decided it would be very nice to ship them this hardware.
But first, the humans used Langley's airplane hangar, the only place with enough empty available space indoors, to assemble the massive structure. That way they could ensure their robot colleagues stayed away would have all the pieces they need to try to put the puzzle together.
DARPA is entering the final phase of its novel orbital and moon manufacturing, materials, and mass-efficient design, NOMAD, program. After checking the feasibility of proposals in laboratory experiments, it is now authorizing small-scale orbital demonstrations. The NOMAD program was established in 2022 to focus on expedient completion of space infrastructure. To do this, the DARPA team behind the program championed the delivery of lightweight raw materials to space where they could be robotically fabbed and assembled in orbit. Illinois researchers are about to start a new phase of Mission Illinois, a study that will send a composite tube manufacturing machine to the International Space Station to produce new materials for space construction. NOMAD aims to test new materials that DARPA and the University of Illinois have developed, which might significantly enhance the near-future robotic in-space assembly process. Quote, "The material carrying process we are using is well tested and understood here on Earth, and the challenge will be to see if we can manufacture it on orbit, in microgravity, radiation, vacuum, and all of the complex conditions in the space environment," unquote, Professor Sama Tawfik said. The team has 18 months to complete this mission, with the last 6 months being dedicated to sending the apparatus into space, connecting it to a small module outside of the International Space Station, and then having astronauts perform the experiments. Quote, "This will be the first demonstration of manufacturing in space," end quote, Tawfik said. Quote, "Realizing such structures will enable the next stage in humanity's space utilization and a future beyond our imagination." Reactive extrusion, when applied to carbon fiber reinforced plastic, refers to a manufacturing process where the polymer resin used to bind the carbon fibers undergoes a chemical reaction during the extrusion process, essentially curing the composite in situ while it is being shaped, allowing for faster production and potentially improved mechanical properties compared to traditional curing methods. This is often achieved by utilizing a reactive resin system that polymerizes rapidly upon mixing with a catalyst or initiator within the extruder. Quoting from the research paper entitled Reactive Extrusion of Frontally Polymerizing Continuous Carbon Fiber Reinforced Polymer Composites. The manufacturing of carbon fiber reinforced polymer composites demands rapid and energy efficient strategies. Frontal polymerization enables the manufacturing of carbon fiber reinforced polymer using dicyclopentadiene thermoset polymer which meets these requirements. In this work, we introduce reactive extrusion of carbon fiber reinforced polymer where two rollers provide localized heat and pressure to sustain the curing reaction and the consolidation of a continuous carbon fiber tow pre-impregnated with dicyclopentadiene. We studied the effect of the extrusion speed, temperature, and compaction force on the properties of the produced carbon fiber reinforced polymer. Mechanical testing confirms that the resulting fiber volume fraction and the elastic modulus are similar to bulk cured tows. A homogenized thermochemical model is developed to study the effects of the process parameters on the polymerization reaction. The process produces hollow woven composite tubes directly via extrusion and in situ curing. Overall, this process offers advantages in curing, tooling, speed, and energy. Quoting from the research paper again, compared to state-of-the-art continuous fiber thermoset composite additive manufacturing processes in published literature, the reactive extrusion carbon fiber reinforced plastic methods described in this paper compare favorably in terms of both printing speed and fiber volume fraction. The tow-based process maintains a printing speed that exceeds that of fiber placement-based direct ink writing of composite tows. Additionally, this process attains printing speeds and fiber volume fractions comparable to those of existing additive manufacturing processes of epoxy-based systems, but without the need for a post-cure in an oven. The reactive extrusion carbon fiber reinforced plastic process is therefore more efficient with respect to the total energy requirements for curing. This can be observed by the 4 orders of magnitude reduction in energy per unit volume for the RACFRP process compared to that of conventional curing in an autoclave. Simply amazing. So here is my summary. The Fighting Illini are leading the way to a space robot built of large, inexpensive, and energy-efficient fabrication and construction techniques anywhere in the solar system. They've already shown how to do it in the lab, Now they will soar on the Northrop Grumman Antares rocket and Cygnus robot spacecraft up to the International Space Station to see whether the reactive extrusion process works reliably in vacuum and microgravity. Microgravity produces some deviations in flame dynamics compared to Earth gravity conditions. We wait expectantly for their flight next year. Omni Futurists.